Hello everyone. This presentation delves into the intricate dynamics of managing data within the rapidly evolving Internet of Things ecosystem. It introduces a comprehensive exploration of how IoT systems handle vast amounts of data, starting from its collection at the device level to its processing and storage across hybrid architectures. The discussion underscores the shift from traditional centralized systems to more agile and efficient frameworks that integrate edge and cloud computing. By the end of the presentation, participants will gain insights into emerging trends, challenges, and future directions in IoT data management, particularly in enhancing scalability, security, and real time capabilities. Let's look at the IoT growth and challenges. The Internet of Things is experiencing unprecedented growth, with billions of devices being connected globally. This exponential increase is creating significant challenges in data collection, storage, and processing. The surge in device deployment leads to a corresponding explosion in data generation, requiring advanced frameworks to handle the diversity and volume of information. IoT ecosystems are inherently complex, comprising heterogeneous devices that communicate through varied protocols while catering to applications with stringent real-time requirements. For instance, in smart healthcare, wearable devices generate critical patient data that must be processed and analyzed in real time to support immediate medical decisions. This complexity necessitates robust, scalable architectures that can address the challenges of integration, latency, and resource optimization. Now let's look at IoT architecture and data flow. IoT architectures are designed with multiple interconnected layers to facilitate the seamless flow of data from physical devices to end user applications. Starting at the perception layer, sensors, RFID readers, and smart devices collect real world data such as temperature, motion, or environmental conditions. This data is then securely transmitted through the network layer, employing lightweight protocols like MQTT, COAP optimized for constrained devices. The processing layer utilizes a combination of edge and cloud computing to analyze the data in real time, ensuring timely decision making. Finally, the application layer presents this processed information through user-friendly interfaces, dashboards, and analytics platforms. An example of this layered architecture can be seen in smart city systems, where traffic sensors feed real-time data into centralized dashboards that guide dynamic traffic management decisions. Now let's look at current data management approaches. So contemporary IoT systems leverage distributed architectures to optimize the placement and processing of data. By combining edge and cloud computing, IoT frameworks reduce bandwidth usage and latency while enabling real-time responses in critical applications such as industrial automation. Fog computing serves as an intermediate layer, allowing local gateways to perform initial data pre-processing before forwarding it to the cloud, which is particularly useful in scenarios like manufacturing where milliseconds can impact operational efficiency. Additionally, microservice architecture decomposes IoT systems into small modular components, enabling developers to independently update scalable specific functionalities without disrupting the entire system. A real-world example includes smart agriculture, where edge-based microservices monitor soil conditions and seamlessly integrate weather predictions from cloud services. Now let's look at data collection mechanisms. Data collection in IoT relies on a diverse range of mechanisms tailored to specific use cases. Sensor network form the backbone of IoT, using advanced fusion techniques to aggregate data from multiple sensors for improved accuracy. Mobile and wearable devices further revolutionize by integrating built-in sensors such as accelerometers, GPS to provide real-time user-centric information. Actuator systems integral to closed-loop IoT setups not only collect data about environmental changes but also execute automated actions based on feedback. For example, smart irrigation systems in agriculture adjust water levels based on sensor readings, ensuring optimal resource use and crop health. Now let's look at storage infrastructure and solutions. IoT storage solutions are evolving to meet the growing demands for scalability, speed, and efficiency. Cloud based storage provides vast capacity, supporting petabyte scale data volumes with advanced features like geographic replication and tiered storage to balance cost and performance. Meanwhile, edge computing offers local storage with ultra low latency, essential for applications requiring real time data access, such as autonomous vehicles. Hybrid architectures further enhance this setup by intelligently orchestrating data placement between the edge and cloud environments, employing machine learning algorithms to optimize cost and access time. For example, a hybrid storage solution in a smart home system may store time sensitive security camera footage locally while archiving historical data in the cloud. Now let's look at some processing methodologies. IoT data processing is characterized by the need for both real time and batch analysis. Batch processing excels in analyzing historical datasets using parallel processing techniques to uncover trends over time. Real time system processing, on the other hand, handles continuous data flows leveraging in memory systems for low latency responses. Machine learning applications have become central to IoT processing pipelines, enabling predictive analytics and anomaly detection. For example, in predictive maintenance, ML models analyze IoT sensor data to detect early signs of equipment failure, allowing preemptive interventions and reducing downtime. Now let's look at some technical challenges in IoT. Despite advancement, IoT faces significant challenges including integration complexity due to diverse protocols, platforms, and legacy systems. Real-time applications struggle with latency management, particularly in distributed architectures where network conditions fluctuate a lot. Resource constraints such as limited processing power, memory, and battery life further compound these issues. Addressing these challenges requires meticulous optimization strategies and innovative technologies to ensure IoT systems remain functional, scalable, and efficient. Coming to emerging solutions, emerging technologies are paving the way for overcoming IoT challenges. The deployment of 5G networks revolutionize latency and resource allocation, making it easier to support IoT applications that demand ultra low latency and high reliability. Containerization and microservice architecture simplify integration and scaling processes, while energy management innovations extend device longevity through harvesting and efficient battery technologies. Edge intelligence combining AI and ML at the edge enables autonomous decision making, as seen in autonomous drones analyzing data locally to navigate complex terrains. Now let's look at some future research opportunities. This slide on future research opportunities highlights key areas that demand further exploration to address the challenges and harness the full potential of IoT systems. So, autonomous systems are self healing networks powered by AI, minimize human intervention. For example, IoT systems in space exploration can autonomously reconfigure to maintain functionality during unexpected events. Advanced analytics in privacy preserving distributed learning models ensures secure data enabling insights without compromising privacy. Sustainability designing energy efficient architectures with renewable energy integration can significantly reduce IoT's environmental impact. For example, solar powered IoT devices are being deployed in remote agricultural fields for real time monitoring. A pivotal area is the development of quantum safe cryptographic algorithms. These algorithms are crucial as the advent of quantum computing poses a significant threat to traditional cryptographic methods like RSA and ECC, which rely on factorization and discrete logarithmic problems that quantum computers can solve efficiently. Quantum safe cryptography, also known as post quantum cryptography, focuses on algorithms that remain secure against both classical and quantum attacks. Examples include lattice based cryptography, hash based schemes, and code based cryptography. These methods rely on mathematical problems such as finding short vectors in lattices, which remain computationally infeasible even for quantum computers. In the context of IoT, the need for lightweight and energy efficient quantum safe algorithms becomes paramount. As IoT devices often operate with constrained resources, future research should focus on developing scalable, efficient implementation of these algorithms that can be integrated into the IoT ecosystems without compromising performance or power efficiency. Additionally, research community must explore protocols for transitioning existing IoT systems to quantum safe infrastructures to ensure long-term data security. So in conclusion, the hybrid architectures, edge intelligence and advanced machine learning methodologies have transformed the way IoT systems collect, process and store data, making them efficient and scalable. However, challenges in integration complexity, resource constraints, and real time processing persist, requiring innovative solutions. Looking ahead, the integration of quantum safe cryptographic algorithms is a pivotal step towards securing IoT systems against future threats posed by quantum computing. Coupled with advancement in autonomous systems, energy efficient architectures, and privacy preserving analytics, these innovations will shape the next generations of IoT ecosystems. By addressing these challenges, the IoT landscape can achieve its full potential, enabling transformative applications across industries while ensuring security, scalability, and sustainability. I hope you like this presentation. Thank you.